I will start maybe this first hour by trying to explain the title, explaining what it is about and what it is aiming at. So it is a lecture, but it is also about an ongoing project. So I will maybe give the references if you want to have a look on the website. But in a nutshell, and then I will expand on that. What we want is, first, there is a series of infinity categories. So infinity categories, it is a generalization of category theory that designed so that all homotopical methods arise naturally. In particular, you can interpret all classical category theoretic constructions in there, except that now the output will be automatically homotopy theoretic. For instance, if you want to do a sheaf cohomology, it means you interpret your favorite ordinary topos in there and then take global sections in there. But now the output will be the derived version of global sections, which is exactly what you want for cohomology. And to develop such a thing has been a trend since the last quarter of century, say. Because, for instance, if you want to do derived algebraic geometry, or either for the sake of itself, or to use them to understand stable homotopy theory, as people like Mike Hopkins and Jacob Lurie did, you need to implement a lot of non-trivial mathematics, but interpreted in this new version of category theory with infinity in front of it. And one of the problems with infinity category theory is that it is hard to construct if you do it from the point of view of classical mathematics built on sets. And so what you do is you provide set-theoretic models, and their manipulation is complicated. And also you have many different models that are equivalent, and then comes the problem of finding what properties are intrinsically defined in infinity category theory and which properties are defined on the model and stuff like that. And so this theory was designed to answer this kind of question. It is nowadays, I think, a well-established part of mathematics. But up to now, it has been constructed within classical mathematics, built from set theory, and on the top of everything. So in some sense, it is extremely sophisticated. Yeah? That's not something you can teach to a first-year student at all, not even a third-year student. Yeah. On the other hand, there is homotopy type theory. So calling as hot. This is a way to do logic, like literally logic. It is a kind of dependent type theory in the sense of John Cartmel, and it has its roots much earlier from the work of Bertrand Russell, and then after in computer science, Church and many other people. And so it is a way to do a type theory in the same way you would use in computer science if you want to develop a proof assistance and things like this, for instance. And but the main thing that appears here is that we really want so I will also expand on this. For the moment, it will be just a word. But there is univalence in there, and univalence is a way to declare that there is only one way to identify things. I will come back to that, why it is a natural question and why it is a little bit brutal, at least at first, to claim that. And then within infinity category theory, there is a notion of infinity topoi. And it has been a folklore result, and it became a theorem after the proof by Mike Schulman, that you can interpret homotopy type theory literally in any infinity topos. That means for any infinity topos, you can find a set theoretic model, which would be an actual one category, and you can realize homotopy type theory as a semantic interpretations in this model. Yeah. So in some sense, if you want to say that there is an infinity analog of classical mathematics, so there is an infinity analog of what you will see in the lecture of Marc Aguier, That is, you can do infinity topoi and do infinity logic and so forth. And in some sense, so the idea that each category defines its own logic. And so the folklore thing was that this language of homotopy type theory is the language of the associated to each infinity topos. But if you want to be precise, what people really understand is this. So far, to my knowledge, no one understands what an elementary infinity topos means. Yeah? Of course, since we know that Grothendieck topoi should be elementary topoi, and we have plenty of examples of infinity topoi like this, so we have plenty of examples, but what is the actual definition of that and what it is all about is slightly more complicated. In particular, the difficulty can be seen from the fact that if it were the case that we understood what it means, then from an homotopy type theory, that is language of some abstract infinity topos, whatever that means, we should be able to develop all of mathematics, because that's the point of having a topos. It's like it's supposed to be the analog of your sets or whatever, and so you are supposed to be able to do everything out of there, and that should include, at the very least, category theory. And if you do the homotopy version, that should be infinity category theory that you should be able to do. And to go from this, the pure homotopy type theory, to higher category theory is what is elusive so far. People don't know how to do that. And so in this precise sense, we do not know what is an elementary infinity topos. But of course, if you have a Grothendieck infinity topos, then you can do infinity category theory inside it. And actually, there is a very nice work by Sebastian Wolf and Louis Martini. And you can look at their work on the archive, and it consists literally to develop all of infinity category theory internally into any Grothendieck infinity topos. That's very nice. So what this project is all about, and I will try to explain how it goes, is it wants to do both things all together by definition. So to solve the problem of going back and forth just because it doesn't occur anymore as a problem, ever. Okay. So that means that the goal is to develop the logic, not because see, if you think of a topos, it's about the logic of sets somehow. If you do the logic of infinity topos, it's the logic of the infinity analog of sets, which are homotopy types. And here, what we would like, if you want to do also infinity category theory, it means you have to develop the logic of category theory, or even better, of infinity category theory. So we want to define what that means. And when you say logic, you want to say that in many ways. So it should be foundations for mathematics. And I really mean classical mathematics at the very least. You should be able to use that to do everything and without changing even a comma in Voevodsky and stuff like that. Yeah? It should be possible to just do that. I said I am a mathematician, so I want to just do mathematics at the very least. But so I would say what I intend to include in what I mean about doing mathematics. So and so that should mean you should be able to do category theory. And that includes a few elementary things that you want to have to begin with. And you should have something called the Yoneda lemma. Then you should be able to speak about limits and colimits of Kan extensions, which is a generalization of both. And then you want to say what it means to freely add limits and colimits, and then to compute Kan extensions. And once you have that, you will have a way to produce categories by generators in relations that are called presentable. So I should put infinity or yeah, whatever categories. And presentable categories are these nice categories in which every naive statement that you want will be true in terms of category theory. For instance, you would like to be true that the property for a functor that it commutes with limits would be equivalent to the fact that it has a left adjoint, which is false in general, but in practice it is true. And presentable categories is a setting where this kind of statement is true. Yeah? It is why it is very convenient. And the other reason why they are important is that anything defined by an explicit construction will be presentable in this sense. That's why in practice, who cares about the difference between having an adjoint or preserving limits? And then presentable infinity categories are important because then you have the notion of topoi, infinity or not. Because topoi, they are defined as being presentable infinity categories that are locally Cartesian closed and have a kind of a subobject classifier, for instance, if you want to have a one topos. And there is a similar characterization of infinity topoi as presentable category, so a natural continuation is that. Then you want to do K-theory. K-theory is very important because that's the most basic way to do measure theory, to count finite stuff. Yeah? And so you want to be able to do that. Even though in some homotopy theoretic sense, that's extremely hard to compute. Yeah? You only compute very low-level stuff, which is what counting is about. And then there is a higher things that are very interesting and also mysterious sometimes. And then you want to do possibly derived or not algebraic geometry. And maybe more than that. But by doing mathematics, I want to include at the very least everything in this list. But what we want to do is actually logic. And then there is what we discussed already, the fact that in Mark Egge's talk is that so you have to you can discuss semantic interpretations of theories. So the problem is also to have a logic that can be slightly beyond first order theory. And this dependent type theory, and homotopy type theory is just an instance of dependent type theories in general. There are some kind of well-behaved higher order logics, yeah, that, of which you can try to find models and stuff like that. And so the theory we'll develop will be built on this kind of principles. But the idea is that if you look at it, so how do we build semantics, in particular in categorical logics? You take your favorite language with sorts and lectures and so on and so forth, and then you build a category out of it, and then you look at functors from this syntactic category to some nice category of sets or topos or whatever. And that means that in some sense you are taking your logic and you are using another logic, another at least formal language, which is language of sets, and then you produce models within that, because you have decided, I would say we have decided as a community, mathematicians, that to validate something is always through sets. Yeah? But there is something about the fact that synthetic category theory will validate itself. You don't have to go to set theory anymore, ever again. So it doesn't mean you cannot go to sets. I just said that you don't have to. And maybe in some sense, why do you use set theory to produce your semantic interpretations? It's because you interpret category theory through set theory, then you construct categories using these very semantic interpretations of category theory. And you see categories are sets of objects, sets of maps between objects, and so forth. And why would we say that you have sets anywhere in a category? This is a question we could ask. And the reason we have this, and we come back to that, is that we'll develop a logic, a type theory, so there will be types, but then we'll decide to call types categories. That means that from the point of view of the logic, you don't have to define what is a category, or in fact even a synthetic or infinity category, because any type will be that. So any well-formed statement, whether you understand it or not, will be a well-defined category. you never have to wonder if something is a well-defined higher category. And there is a very important example of a category, which is there is the synthetic category of synthetic categories. That is an object of your theory that represents everything you want to know about it. And since your semantic interpretations are defined through the language of category theory, and here there is nothing else, or there will be nothing else, it will be a tautological way to do it. And to come back to the title, which speaks about topoi, this is exactly where this will be about. So maybe before doing that, I should say that it will validate itself, but it will do more than that, because we will be able to define what is an elementary topos within that. And by definition, and this is what I'm about to at least to explain what will be the spirit of the definition, and then come back to it maybe later on. In an elementary topos, you will be able to, it will be a semantic interpretation of the theory of synthetic categories. So in fact, it does not only validate itself with the given category of categories, it validates itself in many ways through all possible topoi within the theory. And these validations so can reconvey the classical ones if you still want to interpret things through ordinary topoi, through ordinary category theory. It will make sense. Yeah? It's not the idea is that we don't want to throw away any kind of idea or methods. Yeah? It's just we enlarge the perspective. Yeah. So to about elementary topoi. So why this has something to do with defining category theory right away. So if you take now, I propose to just come back to ordinary mathematics now. So if you take, I don't know, E to be elementary topos. So in particular, it is an ordinary one category with, it has finite limits. Yeah? And if you have finite limits, you have a terminal object, good for you, and then it is exactly what you need to define what is a category in there. Because it means you can define cat E, it is the category of internal categories in E. So either you define it, if you're a logician, you define the first order language of category theory that we have seen this morning, and then you can look at all models of this language in E. Or, equivalently, see what is a category? C, it is a set of objects. So it consists of this kind of data. So an object of E called the objects of C. Then C1, it calls the arrows or morphisms of E. Then to any object, you are supposed to be able to define the identity of this object. So you have a map called identity. And then to any morphism in C, you are supposed to know what it means to take the source and the target. So a category, you see, it's just something like that. And then you are supposed to say that if you look at the fiber product So here I really mean that it's a set of, the object of pairs which consist of 2 arrows, but you ask that the target of the first agrees with the source of the first, so it is a fiber product, but they exist because you have finite limits. And then you have something called the composition law. And then the only thing you ask is that this identity is indeed an identity for this composition law, and this composition law is associativity. Yeah? So, and then you can also define what are functors and so forth. So you know what this means. And you can go backwards, because you see, whenever you have a category, you can try to define the logic of this category. So you define types or sorts or whatever to be the objects. Here it would be the object, would be the categories in E. And you develop the logic of that. And if you develop this logic, you will see that in the category of categories, a very important aspect is that you have a category of functors. That is, maybe I will come back to it. So you see, you have if you have 2 categories, you want that having a functor like this is equivalent to have a functor from A to the category of functors. We could also denote it this way if you want. But, I mean, if I do categories, I like to call this exponentiation just the category of functors from B to C, and so forth. And so you see, you have a logic of that, and then you have a particular object. Because if you are in an elementary topos, you have finite coproducts, and with that you can produce a very particular object, which is the interval delta 1, or maybe, I don't know, yeah, so it's just this kind of, the category associated to this total order. And this represents the idea of arrows, that is a functor out of that to C is the same thing as a global section of C1, yeah, to just take a morphism. And then now you can, and you know what it means to compose and so forth. So you can say what it means that all morphisms are identities in C, for instance, and stuff like that. So you can say what it means that, in fact, of course, so every object of E defines a category when you have only the identity. So the object are you have an object X in E, you declare the set of the object of objects to be X itself, and you only have an identity. So you define essentially, you have the situation when C0 and C1 are equal, and all these maps are identities. And this gives you a class of categories that are very specific. And these categories, they are exactly the object of E, and the functors between them are just the morphisms. So you can really reconstruct, using the internal language of this category, the category E itself. That means that in ordinary mathematics, it is really the same to understand the logic of E or to understand the logic of the category of categories in E, because you can go back and forth. Yeah? Here I just explained how to go from E to cat E. In the other direction is even simpler somehow. It just consists in forgetting some information, and then you observe that you don't lose anything. Okay? And the main thing that prevents people to go back and forth between these two things is that, because, sorry for the, I don't have Larsen, but is that if you replace ordinary category theory by infinity category theory, we don't know how to go back and forth like this. It's very easy to define, you can define, and in fact, we don't even know how to define this cat E. So the idea is that if you believe that in whatever you call a topos, you are supposed to be able to do category theory within that, whatever that means, it means that what you could do by solving the problem by definition is that instead of trying to understand what is the language of E, you could try to define what is the language of cat E, forgetting that you have E. Yeah? So you just have a category and you want to understand what does it mean that it is of the form cat E for some topos E. And then you take this as a definition of what is a topos. Yeah? And in some sense, the formal language we are developing is doing that. It is a language of something that wants to be the category of categories, but in secret, it wants to say it is a category of the category of categories internal into some higher topos. But because we say nothing about being presentable and stuff like that, we allow things that are not presentable, and therefore that would be analogs of elementary higher topoi. Yeah. And there are examples, including in this theory of infinity categories, that are not presentable that you can build. They exist. Okay, so that would be yeah, something maybe I should have written that. So I said it out loud, but I can repeat it and write it in CS. So it has so semantic interpretations in any elementary synthetic infinity topoi. And here, when I say, oh, sorry, I'm sorry for that. So if we will be able to define the analog of Grothendieck infinity topoi, and this will be, we have plenty of examples because we can take pre-sheaf categories, sheaf, and so forth. So we have lots of examples, and so part of the theory of infinity topoi is that it will be an elementary topos in this sense. So in particular, what I mean is that part of what we should prove when we say that something is a topos is exactly this sentence. Like we will interpret all of category theory within your Grothendieck topoi. And so this work of Wolf and Martini is a proof that at least in classical mathematics you can do that. Just maybe a final remark about semantic interpretations is that, you see, so I'm claiming that we can get rid of sets and so forth. But also the reason why we can believe in such a logic is because the effort to interpret this logic, by which I mean to provide a semantic interpretation of this kind of logic in classical mathematics is already done. Yeah? Even though this project is not finished, but the semantic interpretation is already done. And it is literally what infinity category theory done classically with the work of Joyal and Lurie is all about. And so to prove all the axioms and so forth, so it is essentially, so I wrote a book on higher category theory, and then a joint paper with Kim and Nguyen, the first author here. And these two things together, they are exactly this proof. Yeah, so on the other hand, so if you are afraid or concerned by the fact that we should validate all this within set theory anyway, this already exists, and that's why we can also safely decide that we can explore the axioms and do whatever we like and have this self-contained logic. Okay. So now I will erase, and I will try to explain slightly more what all this is about. Or maybe something again I forgot to say about this is that about the part of logic, so you want to provide semantic interpretations, and it has something to do with providing semantics and so forth. And if you look at what we need to do these semantic interpretations, there are a lot of rectification problems you have to solve. If you read papers on empirical logic, people rectify stuff all the time. Yeah? And they discuss how we should do it and what is the best way and stuff like that. And that is indeed a serious concern. And what is at stake and what is used all the time is the fact that you can rectify a Cartesian fibration into a functor into the category of categories. And this is also something that is part of what I just erased. So what we use in classical mathematics, so the common tool is in classical mathematics, people who do infinity category theory, they call that straightening and straightening. So by common, I mean common to logic part and the mathematical one. If you want to distinguish them, I mean, you don't have to. Okay, so straightening and straightening. And that is the correspondence between co-Cartesian fibrations over some category C and functors of type C to cat. Yeah? And this is a very, very central part. And now what I would like to discuss is to go back slowly to what is the type theory a little bit, not with the full detail of the rules of syntax and so forth, but to explain the part on homotopy type theory, and then to give you a glimpse, maybe I think in the second part at least, about category theory itself. But that is a common tool, and what is somehow this is a very non-trivial problem to define that, because when you say you have a correspondence, we would like to say that these two sides, they define objects of the same type, and therefore should be allowed to compare them, and in this sense they should be equivalent in a precise sense. And if you do classical mathematics, this is not true. It's not a big deal. I mean, we have done mathematics at least for a century dealing with that, but and the main difficulty is that essentially these two things as ordinary one categories, they are not equivalent as one categories. And so you have to go to consider, in classical mathematics, you have to consider them as two categories, and then develop the notion of equivalence of two categories, and then see that they are equivalent as such. But then you see that in terms of purity of language, that's a problem, because you start from, you see, if you want this idea that you validate yourself, so you should have a language that is conservative enough, you want conservativity, and you want to say that the same language is used once and for all. And what is happening in ordinary mathematics is that you cannot have this conservativity. You have to climb a ladder of complexity. And you have it because this equivalence, you want it. I mean, there is no argument to have. Yeah? You need it. So you climb. But what is at stake is that univalence, that I will discuss in a few minutes, is subsumed by this principle, at least in this synthetic way, because we will enforce that this equivalence holds within the language we have been working with. And the point is that the fact that we enforce this will prevent your logic to be classical, in the sense that, again, there is a dependent type theory within that, underlying all this, so that means there is an actual formal language, and it has a lot of axioms after that, and 90% of the axioms, you can interpret them without a change to ordinary category theory. You see, you will be allowed to interpret all types I will introduce as ordinary categories. All objects I will introduce as ordinary object of ordinary categories and so forth, and it will be sound for very, very long until I will claim that. And then suddenly, the semantic interpretation within ordinary category theory won't hold anymore. And that's where you have to go to infinity. But the gain you obtain from that is that the language is the same. So in some sense, you will learn how to manipulate the very language of category theory you are already used to. You don't have to construct higher categories in a new way, or it looks like ordinary category theory. It's just that with an extra axiom, you will have this kind of equivalence on the nose, and therefore you will do infinity category theory effectively, because this is the only semantic interpretation you will be allowed and able to produce. Provably, you can really prove that this axiom is just, you can interpret that in any topos, as I said, and if you interpret this axiom classically, the topos is a sheaf on the empty set. I mean, that's what I mean by provably. So if you want a non-trivial thing, you will have to go to infinity. Okay. So now I will spend some time on dependent type theory. So I won't define it formally. I will let you have a look. But that is very close to what we are doing in Mark Egge's lecture. So, because all this is the development of this, so it dates back to Bertrand Russell, so first as a kind of hygiene to do mathematics without having the Russell paradox, but then also as an actual foundation of mathematics. Yeah? The Principia Mathematica, it's an attempt by Russell and Whitehead to actually produce all of mathematics, somehow trying to do Voevodsky by themselves in the 1910s. Yeah? And they didn't succeed completely because it was a little too early. But it's really a very serious thing. And then, it is less popular among classical mathematicians, but in computer science, it is at the, lambda calculus is a kind of natural continuation of it. And then logicians and computer scientists have developed that very far. And again, so the idea is that now that you know more or less what is an elementary topos, so the idea is that you want to define a logic when types can be interpreted as object of your favorite elementary topos. So in some sense, you could also declare that your types as some kind of sets. Yeah? But if you think about it, the way elementary topoi are constructed, they are just categories, maybe with finite limits or an internal home and stuff like that. And then you add more and more axioms or structure to it. And so you have a very general theory of logic that are more general than what you could do in an elementary topos. And dependent type theory is a way to do that. So if you look at semantic interpretations, they have a name. They are called GAT for generalized algebraic theories. So if you want to learn the theory properly and say that you don't want to wave hands the way I will do now, you have to Google this kind of keywords. And the person who developed that very carefully is John Cartmel. So this is from the 1970s or something like that. That is something that looks like a very stable way to say what is a dependent type theory in general, much more general than what you would get with a topos. Yeah? And that's the point. Once it is general enough, you can add more axioms so that it becomes actually the internal language of an elementary topos or not. But for the moment, I propose to forget about what I just said and pretend that we are aiming at set theory somehow. Yeah? So it's a language when you have types and terms. Yeah? You have two kinds of things. So I will write types with capital letters in any alphabet I know. I will use Latin mostly. Then, terms with small letters. Yeah? Also little x, little y, and so forth. Okay, and actually there is also something more that, because I won't be very formal, so to be precise, you have also context. Yeah? So you have these three things, but we'll pretend it's the same as types. Yeah? Because it doesn't matter that much. And then in this logic, you have to say what to do. And basically, you have judgments. This is what you do. And the idea is that a term, you cannot speak of a term abstractly. This doesn't make sense at all. That's the basic of type theory. Yeah? You have a term is always assigned with a type. So when you declare a term, it must be of a given type. So for instance, I have a type capital A, then I can speak of a term of type capital A. And then I can produce the judgment that such a term is well defined and available in my language. Yeah? That is the basic, this is a judgment that A is a term of type A. And so that the basic judgment you want is that. The other kind of judgment you want to know is what he calls definitional equality. I won't even write it down. I mean, sometimes you can write, I mean, you write it down either this way, but this I don't like because you use this colon already, so. Because then it would mean that we have a term of type equality. This doesn't make sense. I mean, because so what we want is actually so you just provide a name, so like this, that, or whatever. So something that, and definitional equality, it's just because you want to declare something to have a given name. It's just a labeling, a very formal one. Yeah, you write A is equal to B because you had A to begin with, and you want to call it B because I mean, why not? Yeah. And of course, there is a rule that you can always label A as A. Yeah, that's, and stuff like that. But in some sense, that is this definitional equality is an equality that is not interesting. It's not the one you would use to provide an interesting equation. Because usually you want to prove A equal B when A and B are not equal by definition. You want a non-trivial equality. This is what we do usually. And this kind of non-trivial equality, this will have the name equality. That is different. Yeah? Because this definitional equality is pure syntactic whatever to produce a syntactic category and so forth. And then, as I said, you have context. So if you have gamma that is a context, you can produce a judgment in context gamma. So what does that mean? So maybe I will go back to more, and then hopefully I will stop there for the syntax of type theory. So what I was trying to convey is the kind of judgment you can do. So I will take it, do it again from, so three, I don't know, not types because types are these, so kinds of judgments. So you can declare that something is a type. Yeah? And this, again, the idea is that all the judgments you introduce, they can be done in a context. All of them. That's the point of, this is what dependent means. You see, you could do all the same axioms with only, without context, and then essentially that will go into the direction of lambda calculus and stuff like that. The point that you go to dependent is really because you allow yourself to change, to produce judgments depending on the context, and you also explain how formulas and truth values behave when you change context. Yeah? But I will explain why you mainly have to understand the empty context, and then I will explain how to do that. But if you want to be formal, so you can say that in some context something is a term. And if ever you have two terms, in some context gamma, that gives you a new context. I won't explain how because I don't want to do syntax, but I just want to say that I want to insist on the fact that so A is defined in context gamma. I have two terms defined in context gamma, and then I can claim that, or maybe I could just do that, I guess. So I mean, assuming so this is the first kind, second kind, and third kind. You can claim that things are definitionally equal. But again, this is not interesting. This is the silly equality that is just there to make things defined. But this is not what you want to prove. Now, sometimes you have to insert such things in proofs and stuff like that, including when A is equal to A. We need tautologies of this form. Okay, and then you have rules that say that. So the idea of if you want to, I won't give you the rules. Let's say no, I'm not even sure we need that. No, we really don't care. Yeah, I should check, but maybe we don't care that we can make types equal, because we do something else, you will see. Then the idea is that, so plus you have some rules and so forth, but what the rule means is that you should interpret there is a syntactic category call it, I don't know, maybe S, like syntax, or not. But so this S will depend on your type theory. And then you should interpret types or contexts are the objects of S. Yeah. And what is interesting is that, so we were discussing about semantic interpretations, and one of the things is that there is always a semantic interpretation within type theory that is given. That is what dependent type theory will be. Is that you can, whenever you fix a context gamma, for each context gamma, there will be a dependent type theory that will satisfy all the axioms, absolutely all of them. And then there are rules also that explains how to go from a dependent type to the other. And it will be through some kind of pullbacks. And these pullbacks, they will want to preserve everything that is available in your logic. And that means that, so whenever you defined, but this is in the absolute context. And in general, so in context gamma, types defined in context gamma, they form a full subcategory of the slice category. It could be everything. That is, if you again, there is there is always you have to produce a non-tautological version of equality, the one we will actually write as two parallel lines. And the point is that in classical mathematics, you have propositions, and the point of propositions is that they are either true or false, and there is nothing else to discuss ever. Yeah, because truth values, they form some kind of you look at only at monomorphisms in your objects. And the point is that if you enforce that the only things you have to say are of this form, that also everything of importance will be propositions, and therefore they're either true or false and nothing else to discuss, then in fact types in context gamma, should be essentially everything, all of it. The fact that you allow to have possibly a full subcategory that is not everything gives you some freedom now that you can use or not. Yeah? To give you an idea is that now, because I don't want to explain the way you construct the syntax, but that's, for instance, but yeah, maybe I will give examples later on. But so maybe the objects of S over gamma corresponding to dependent types of a gamma, dependent are denoted as maybe with a double arrow, say. Yeah? I just need an extra, so because the objects of this are morphisms to gamma, and I will give a precise, a specific, and there are supposed to be some kind of vibrations, some kind of bundles. Yeah? Okay. And then, yeah, once you have this interpretation, now the terms, so call it P, they correspond to global sections of P. So morphisms from gamma to A, S, so that PS is the identity. And now what you can observe is that, what the axioms tell you is that you can do pullbacks of these fibrations, these kind of maps. They exist. That means that the pullback of such a thing exists, and the output is a map of this form. Yeah? And what we'll also add in the axioms is that there is a terminal object, so a type, that corresponds to the empty context, because as I said, context and types are the same thing. So the empty context corresponds to the terminal object in type theory. And yeah. So what I write, I don't write a gamma at all. It corresponds to the terminal object in S. So what I mean is that if you have a gamma prime and gamma and a dependent type interpreted as a morphism, so the pullback will exist. And will be again a legit object of a dependent type. Yeah? And essentially the axioms are there to make sense of what I just say. So if you believe in category theory, you can just also somehow almost define dependent type theory as a category S with a class of maps that you call fibrations or dependent types, depending on what you want to apply as an intuition. So that the pullback of a fibration is a fibration. You will also ask that the composition of two fibrations is a fibrations and stuff like that. Okay, and the point is that all the axioms, so if you write S of gamma as the full subcategory of S of a gamma spanned by fibrations of a gamma, the idea is that for each gamma, this will be a semantic interpretation of your type theory. Yeah? And that's where now you have some choices to make. So in classical way to do type theory, people essentially enforce that all the axioms that they want remain true for all gamma, without any exception whatsoever. And that corresponds to the following thing. So an example, take S to be your favorite elementary topos, or not elementary, who cares? And I really mean in the classical sense. For the moment, I don't want to. How many time do I have? I don't have a lot of time, do I? Yeah, but I can also stop there because I have time later on. So I should stop there. Let's have you have a break and resume at this point. So thank you for that. Thank you for coming back. So I want to discuss the example of elementary topoi. So a way to say it is that there is, because there are a lot of dependent type theories, plural, and there is one dependent type theory whose semantic interpretations are exactly elementary topoi. And in the axiom of elementary topoi, the way we have seen this morning, for instance, it was just Cartesian closed with a subobject classifier and a power set, kind of a functor. And in fact, then it is a theorem that all slices are elementary topoi. And that fits is what I want to discuss, in the sense that you see, we produce a category. The syncretic category will be a semantic interpretation of the logic you started from, essentially by definition. Therefore, if you start from the dependent type theory of elementary topos, it will be an elementary topos. And therefore, all the slices will be an elementary topos. And that means that any proof that you can do that uses only the language of elementary topoi is true in any elementary topoi, and that includes all slices. And this remark is not just a remark like this, it's because that's a very important one. That is what explains that many apparently naive and poor man versions of things that should be proof, and you had only a very elementary version that shouldn't lead anywhere, will be effectively a proof. So, and this kind of trick we will use also in the formation of category theory, but it won't work as easily as this one. So let's discuss this nicer kind of context. So, so you have an elementary topos. So you can interpret objects of S as types, and therefore also as contexts, and put by definition that all maps are fibrations, whatever that means. Because you know that you have pullbacks exist anyway, all finite limits. So this will be a dependent type theory. And now the point is that if you have any context gamma, then you can produce a pullback functor that consists in taking an object X and then take the Cartesian product with it. Of course, you should see this over gamma. So if you want to be precise, you take the second projection. Yeah? And this is a functor. And the idea is that this will be a dependent type theory as well. But this is also an elementary topos. And the point is that now the axioms of dependent type theory, what do they say? Is that first, what is this functor? It is the right adjoint to this functor. So you take anything of a gamma, and you forget that you are over gamma. Yeah? This is what this pullback is about. So the fact that you have fullbacks, you can reinterpret by saying that this kind of functor, which is always defined here, you see, just the fact that it's a functor, it just means that you know how to compose maps, and that this is an associative stuff. Yeah? So the fact that you have finite limits, it is just the fact that you have a right adjoint to this very elementary thing, the fact that you can compose. And the fact that you have an internal ohm, an exponentiation, is the fact that, in fact, this functor also has a right adjoint. Yeah, yeah, it is right adjoint to something, and it has a right adjoint. And in particular, that means it commutes with everything in the world. And by everything, I mean everything. Because you see what are the ingredients of topos theory. You need to speak about finite products, the power set operation, and the subobject classifier. And what I mean is that this operation will preserve all of these gadgets and all the relations between them, in particular, so everything will be true. In particular, so any proof you do here will remain a proof here. Yeah? And then that means that now you can cheat a little bit, because you can say, yeah, okay, I want to prove, so I can tell you how to use that. In some sense, when you interpret terms, you see, when I write this, so if I'm doing set theory, I would like, and I think I'm not the only one, to consider this as an element. And would like to manipulate terms as I do with elements, do my proof and go home. This is what I want to do. Yeah? And then the idea is that if you do it, then that's not true. But also, that's the point of syntax. I mean, it is just a symbol, so I can do whatever I want. And what I claim is that if you do topos theory, one way to interpret this that is extremely sound is to declare that a term like this is just an arbitrary arrow. Going to A from anything. Say, I will say gamma on purpose, but it doesn't matter. It's just the domain of A. And then you see that indeed now a function it takes a term little a of capital A to a term of capital B. And if you can do that for any term of this form, that by the Yoneda lemma, that is indeed the same thing as a morphism. And so that means that, you see, it just means that if you interpret terms as maps, then it looks like elements, whatever that means, or terms, they indeed determine what a morphism is. And then the point is that you could say, okay, but what I really understand as an element is a morphism from the terminal object. Otherwise, I mean, I'm kind of cheating a little bit. But then what all this story is about is to say that you can always do that. Yeah? You can always, whenever you have a morphism, say gamma like this, so little a from gamma to A, and I would like that gamma is a terminal object. So what I can do is, let's say that this thing, I will call it is definitional equality gamma, x gamma. So it just means it is x interpreted in context gamma. See, so if I have something defined in the absolute context, it is also defined in any context I want. And I can specify which one if I want, or I can be lazy and say, okay, it is x in context gamma in words. And depends on what you want to do. And the idea is that if you do that, so you can interpret it in context gamma. Well, now in context gamma, gamma is a terminal object. Agreed? Maybe I should have written it this way. I don't know how you prefer it. So that is another object. Yeah. And now, so if you want to now in this, so now this thing is now my object A in context gamma. And if I want to have a global section, that is a morphism from the terminal object to there, it should be just a morphism like this, so that this commutes, this triangle. But a morphism to a product is by definition of product a pair. And now you have a pair of a morphism to A and a morphism to gamma. But the fact that this commutes says that the second component must be the identity. So because this commutes, there is no choice about the second component. And so at the end of the day, a global section of A seen in context gamma, that is nothing else than just a term. And again, if you have a type theory where all the axioms of your type theory are not only true in the syntactic category, but also in all slices, then you can interpret arbitrary morphisms as simply global sections in the appropriate context. And using this kind of trick, if you have a proof that seems to work only for morphisms from the terminal object, and otherwise you're like, I don't know if it works, in fact, it will be turned into a proof that works in any context gamma, and therefore unfolding everything for any morphism like this, and by some unit argument, it will be an actual proof. And this kind of way to organize proofs really work well, and that's how you can turn apparently very naive things that looks like you are doing very old-fashioned set theory and so forth, work extremely well in any elementary topos, for instance. You just have to learn how to do it properly. But that's really something you can learn, and when you know it, it looks like you are doing, indeed, good old-fashioned set theory, just intuitionistic, possibly. You can also add axioms, which is that it is classical, of course. Okay. So the point is that, of course, you could do with an arbitrary type theory, So you could ask that each of these abstractly given S gamma satisfy all the axioms. This is exactly what dependent type theory is about, the classical one. But you could also be more flexible with that and ask that this will be a semantic interpretation of the type theory you are interested in, for instance, category theory. But you will ask that this is true only for some gamma as opposed to everything. And this you will need to know because, for instance, you see what I just wrote here for S, that you have this has a right adjoint. It is really equivalent to the property that there is you can exponentiate, there is an internal home, which is true for category theory, but absolutely not true for slices of categories, of the category of categories. Yeah? Because if it were true, that would be equivalent to the affirmation that all functors are Condorcet fibrations, and we have a very explicit characterization of Condorcet fibrations, and therefore you can provide a lot of examples and also counter-examples extremely easily. And that means that if you try to do the logic of category theory, you cannot claim that if S is a category of categories, that slices of the category of categories will have all the axioms of category theory. It will still satisfy some axioms, and I don't claim you should get rid of them and so forth, but at least you have to be more careful. Yeah? But apart from this, even if we do it for a constraint, it could be that, for instance, all the axioms are true in S gamma for some gamma, and that means that for terms that are indexed with appropriate gamma, you could still try to play this kind of role. And that is what will happen in category theory if you restrict to groupoid. Yeah? If you slice of a groupoid, the category of categories over a groupoid, it has all the features of category theory. And that means, and in some sense, that means that if you can, and you see in category theory, so terms you don't want to interpret them as elements, but you would be very happy to interpret them as objects. Yeah? So of course, a very abstract term, the way I said, without any constraint on gamma, you could think of it as an object given functorially. And this doesn't hurt. You also want that. But sometimes you want to say that you want to speak of an object, like literally, maybe not functorially, because you don't know yet that you can do functorial stuff, for instance. This happens in actual mathematics. Yeah? So the way you would do is that if you say that this is a groupoid, that would be a way to think of it as an object, but possibly not functorially. You could say that it is already very functorial, and I won't argue against that. But the point of all this univalence stuff and so forth is that there is no way around it. I mean, you have functoriality with respect to all kinds of isomorphisms, and that means that there is no way to I mean, it is a very natural thing to consider as an object anything indexed by a groupoid, and that means we have to put this kind of constraint. So this was just to give you an idea of what type theory can look like. Then what I want to discuss later on also is about this univalence thing. So I would propose to also look at very elementary examples and see what is happening. So I propose to say we use your favorite elementary topos, but if you prefer, just take your favorite set theory, possibly even classical ones. I don't care, because what I'm about to discuss is meaningful also extremely classically. But of course, it doesn't disappear because you are intuitionistic, it just remains. So it is about this straightening and straightening. So in set theory, we don't say straightening and straightening. I don't even remember how we say it. Maybe foundation axiom or something like that, but you will see. Even if I don't remember the name, I will explain mathematically what I mean, and that should be. So if we come back to set theory, and then we would like to discuss universes. So universes means that you want to discuss the set of all sets. Of course, you have the problem of the Russell paradox, but assume you succeeded into solving the Russell paradox, because what you could do is just fix, I don't know, a regular cardinal and look at sets that, I don't know, have a cardinal smaller than this cardinal and stuff like that. Maybe are embedded in it to be sure you have something very small, whatever. And then you call that the set of all sets, and if your cardinal is inaccessible or something like that, it kind of deserves to be called this way. But at the end of the day, so you want to have a set of sets. So it's a set, the elements of which I want to think of as sets, possibly with a size constraint. Why not? If you want, if you have a class of sets, you could take a subset of the class of sets. Okay. Now, if you have a set of sets, if I give you a family, and then I want to call sets only the elements of this guy. And once you do that, you create something that is interesting, because you see, if I'm doing set theory, so basically set theory defines an elementary topos, and therefore sets are types. Okay, so I could apply whatever I want from type theory and so forth, and it's a way to have access to the rules of set theory in a rather efficient way. Yeah, that is so on and so forth. Good. So if I take X to be a set, how do I interpret it as an element of the set of sets? Yeah? Saying that X belongs to this set of sets, what does it mean? It means that you have the set of sets, and so the elements are some sets, and then you can define set dot. So what are set dots? That's very easy. These are the guys that are sets in the sense I want. Sorry, they are pairs. Where so A is a something in the and A is a term. If you do classical set theory, you can declare terms are actual elements and so forth. I mean, I just write these notations because I'm used to type theory, but you can write this if you prefer. I mean, and then, okay, we are doing actual set theory here, so they are the same thing. Okay, then. Yeah, so there are pointed sets if you want. Yeah, and now if I want to say that X is an element, that means I want to think of this as a set. So there should be something called a set with one element. So star is a set with one element. And so I would like to say that, at least in this context, or in the absolute context, I would like to say that there is a guy here. And I claim that to see my abstractly given set, like an abstract type, as an element of this, this is how I should define it. Because then, you see, if I do a pullback, that means that I want to say that X is in bijection with a guy coming from here. Yeah? And what does that mean, that you have such a pullback square? It means literally that for any element here, I provide an element here, and therefore through this map, an element here, that is a set. And then the fact that it is a pullback means literally that and also you see that when you compose, there is in fact, it is a constant map. So it means that in fact you should have a family of sets, but the underlying sets are the same, yeah, because it's constant. And then the elements that are allowed to appear are exactly the elements of X. Yeah? So to provide such a pullback is literally what that means. Okay, so far so good, why not? Now here is a drawback. Because as I said, and so in type theory you have to, there is this definitional equality, and how do you identify things? So as I said, you have a definitional equality, therefore you know what are terms. How to identify terms, but the idea is that then we have to provide in our axioms, something I didn't so far, a way to say when two terms are the same in a way which is not tautological. You have to define what that means. So even if you do ordinary mathematics, that is, this notion should be a proposition, that is, two things are equal or not, and there is nothing else to say. So how do you do that? The idea is that you take, so if you have a type, or set, that could be for any type, then how do you define equality? Well, there is the diagonal, which is part of the adjunction because you have final products or something like that. Yeah, maybe it's co-units or something, but it doesn't matter. And it consists of a pair that consists of two copies of the identity. And the idea is that, you see, you can think of it as a map. So you can think of it, it is in S over A times A. You see, that is a map. Yeah? And now the idea is that if you are over that and you are doing elementary topos theory, so this is an elementary fibration, you are allowed to take pullbacks. In particular, if you have any map that is in fact a pair, I don't know, little x, little y, then you can take the pullback. And the pullback, that's a definition now. Yeah? I'll call x equal y. Like this. And now I have a type, and this type you can check, it is indeed a proposition in the sense that because that's a monomorphism, therefore that is a monomorphism, and therefore that is really a subobject of the point. So it is in your Heyting algebra and so forth, and it is a locus where it is true that they are equal. And the fact that it is actually true means that this map is an isomorphism. Yeah? And now that you know what are terms, you see, it means that now, when you do that, you can also define the type of isomorphisms between two sets, or bijections they are called, yeah? Because what you do is that you can look at, you have if you have two sets, I don't know, A and B, so you can exponentiate, so you have the set of maps from A to B, yeah? And then you can look at sets of maps from B to A, and then you can write through equations, that means through appropriate pullbacks, that you take the subsets of maps which says that you have a pair of maps that are inverse to each other. Yeah? It will be a subset. And it will be defined by equations, I mean, using the language of type theory, in fact. You can do that in any type theory. As long as you have this internal Ohm, of course. Yeah, and now you can look, if you have or maybe another notation is this sometimes. Yeah, so it is the same as that, I don't know. Because again, you have to realize that if you, so that's called the Curie-Howard correspondence. So we provide statements. Statements are types. In particular, here there should be sets or objects of your elementary topos. And saying that your statement is true it consists in providing a term in it. And so if I write this without a term, it's just the statement. And that means it should be a set. Yeah? Because this is a collection of all bijections from A to B. Okay. And what I mean is that now, and so to define this, I needed this notion, because how do I define being invertible? It just means that you have a pairs, Fg, but I still have to say these two things. You see, the equation that defines this subobject, it's a pair of equations, and it is here, and this equality should be exactly that. So what I mean is that when I say this, it should mean that and these are types, so you should say it's a product, in fact, because you see this is an element of this product is a proof that these are equal, and a proof that these are equal. Yeah? And so elements of these sets, they are exactly proofs that the pair Fg are inverse to each other, and so forth. This is what kind of thing you would use there. So what I mean is that in the definition of this, you need to define what it means to be equal in a non-trivial way now. Yeah? And that means now that you have two ways to identify sets if you think about it. Because you see now, if you have sets, so maybe I will write it here. If I think of them as elements of the set of sets, whatever that means, that means I can produce this type using this kind of techniques, replacing A by the collection of sets. Or I could play this game. And here, in set theory, they are indeed different, because this is really the type we say that two sets are equal in the sense that they have the same elements, which is a notion we use in set theory, of course. And this is the kind of identification we say that they are the same because there is a bijection from one to the other, which is also something we use, but they are not the same. So these two sets are related because there is a map like this. And it is only a monomorphism in classical mathematics and certainly not an isomorphism. Yeah? So there is a canonical inclusion, but not an isomorphism. And so, in some sense, everything I said, you could do in any dependent type theory when things make sense. So you need to have exponentiations, products, and so forth. You could try to define this and so forth. But then you have this map. And then, in fact, the fact that this is invertible, it can be an axiom. Because you could also claim this axiom in any context and so forth. You could play this game very much. And that is what univalence, in the sense of Voevodsky, is about. But the point is that if you try to interpret this axiom, that claiming that it is an isomorphism, classically, this is false, unless the empty set is isomorphic to the point, which you could also add as an axiom. But it's the only way to have this isomorphism classically. Yeah? And so maybe that's where I should give another interpretation of this dependent type theories. Yeah. So, would like a version of type theory where this thing is actually, with this notation, the same thing as that. And the proof would be through this map. Yeah. And this is Voevodsky hot with univalence. So I propose just to give you an idea of what it is classically, so that you you can interpret it. So the idea is that it's not possible to have this and to define equality this way. We need a non-trivial notion of equality. Of terms. And of course, if you change the notion of equality, remember that to define this, I did use this notion. So if I change this definition, I will also change this definition. Because otherwise, in fact, this definition will be the same, except that equality will be the one I defined earlier. So, and the idea is that, so in a type theory, you will always ask that you have this product. So far, so good. But, and therefore you have the diagonal. And the idea is that you see, so how do we think of it? We think of the equality between terms of A for all possible terms. It is in fact a type in context A times A. Yeah? So the idea is that instead of having this very type, we could fix another one that we don't force to be the diagonal. And I propose to call it P of A, or I don't know. maybe, but it's not of identities. So yeah, people if you open a book on type theory, it would be called identity type. So you could call it identity of A, but I put a capital I at least because if you write identities, this is small i's. Here anyway, it's not the way I write it. Usually I write identities myself with ones, but I don't know, never mind. So maybe I should have done that. So I mean, this is really an object, yeah? So it's not the same as a morphism. It's just something that is in S of A times A, when S is your syntactic category. And then a map like this, that is called RA, that is called R, like, or sometimes it is called refl of A, like reflexivity. Yeah, it's just saying that, of course, you want to know that if you have a term little a, it is equal to itself. And whatever your definition is, this should be true, and that's the proof. Okay? And then, of course, you need more axioms because you want that equality is transitive and reflexive. And, I mean, reflexive, I just say already, and symmetric, I guess. Yeah. Yeah. And that means you add essentially as free as possible in your syntax. That's what syntax does. It is free. That you have this transitivity and symmetry. And how do you do that? Well, the example. So I would like to say space and do classical topology, but the category of spaces is badly behaved. So either add some fancy adjectives so that it's almost okay, but then at some point it will break anyway. I don't know. I don't know any model of spaces that works perfectly well for everything I want. So you have to take a model of homotopy types of spaces that is categorically okay. So a classical one consists in taking simple sets or anything like this. So if you consider, so I will maybe recall what are simple sets. So you have delta as a category of simplices. So the objects are things of this form with n non-negative, and morphisms are just non-decreasing maps between the sets. Okay, and a simple set, it is a category of functors to the category of sets. So here this set is the category of sets as opposed to what I wrote before, but and yes, and then within that you have Kant complexes. Yeah. So remember, should I define what is Kant complex? I don't know. So X is Kant complex if. So you could believe me, this is a topos, so you can exponentiate. So I will define everything else, but this is a trivial fibration. So I will define what all this means. So first, delta n is a thing represented by a simplex. Then now, if you, this one is that you have a map from delta 1 to delta 2, delta 1 to delta 2, and here you have the one called delta 2, 1, delta 2, so what, 0, 1, 2, and delta 0. So this corresponds to 0 sends to 0 and 1 to 1, I guess. Yeah. And this one sends 0 to 1 and 1 to 2. I hope it's okay. So what it's supposed to do is that, and here you have delta 0, and here you have 1 and 1, I guess. No, 0. And then you do a push out of some kind. At the end of the day, so having a map from delta 1 is having a 1 simplex. That is an element of, if you have a pre-sheaf, you can evaluate at 1 and take an element in x1. And then you can look at 2 simplices as well. And 2 simplices of, you could think of them as a commutative triangle. So if you have a 2 simplex, it is in X. Then you have 3 faces, and so basically what this guy is doing, it is taking this part only, as through these restriction maps. And this trivial fibration means that whenever you have a monomorphism and a commutative square like this, you can find a lift like this. This is a brutal way, but otherwise you can forget about this definition if you don't know it. What it means is that you want to interpret these simple sets as spaces. Then you want to interpret one simplices, that is, if you have X, it's a pre-sheaf on delta, so you can evaluate at n equal 1. And you think of this set, X1, as a set of passes. And Kant complexes are just there to say that you can compose passes and so forth the way you would think. That's the definition they do. And technically it goes through these kind of things, but it just means otherwise you could think of a topological space, an actual path in terms of continuous map from the interval. Yeah? And everything is made so that you can compose them the way you think. But then, see, so maybe I should have done it the way you suggest, because then I have to define fibrations, because I have to define, okay. Maybe I'll do that anyway. So we can define Kant fibrations a little bit like that, actually, but actually there is a definition along similar vein, but I don't know if you will like it. But maybe I will do that because that's a way to not to introduce too many things and still to have some definition. So if you have a map, there is a relative version of Kant complexes. And they are called Kant fibrations. So you look at a map from X to Y, and you would like that when Y is a point, you would like to express exactly this kind of condition. So what you do, so you observe that by construction, you have this inclusion, because I did this push out and so forth. I mean, you have to check, of course, that the comparison map here is a monomorphism, but for what I want to say, that's not really important. So there is a map for sure, and you can check it is a monomorphism, but it's not really important here for the moment. And then you can exponentiate, so you can do x to the delta 2, and y to the delta 2, and x to the horn, and y to the horn. And because exponentiation is functorial, so this inclusion, you call it I, this gives you a map like this, and P gives you a map like this, you call it P lower star if you want, I don't know. And therefore you have a comparison map between this x delta 2 to the fiber product of these things, so x to the horn, fiber product with y to the delta 2 over y to the horn, whatever that is. And we'll ask that this is again a trivial fibration, by which I mean again that for any monomorphism you can lift like this. If you don't know the definition, again that is very brutal, but if you have heard of homotopy theory like Serre fibrations or something like that, it is the analog of Serre fibrations in this context. It means exactly that you can lift passes and stuff. And nothing else, in fact. It's really designed to mean that. Okay, and now, if you define S to be the subcategory of Kant complexes, and you have gamma, which is a Kant complex, then you can define S gamma to be the full subcategory of Kant fibrations of this form, x to gamma, as a full subcategory of is a slice. And what I mean is that then you can prove that Kant vibrations are stable under pullbacks and so forth. So it is a type theory. And so this is a dependent type theory. And then how you define the non-trivial identity? Well, so if you take A to be a Kant complex, this is defined as simply the exponentiation A to the delta 1. In other words, it is a space of passes between 2 points, arbitrary points. And then you see that now, if I write it this way, in this interpretation, you still have source and target because you can evaluate at 0 or 1 here. And by definition, that's a Kant vibration. That is not too difficult to prove. Also, maybe not a direct. Now, you cannot see it by looking at the blackboard. Just do some combinatorics that I won't do. It's not difficult, but it takes more than 1 minute. So, so I wouldn't do it by head neither. But you can prove it very easily. So that if you take your time, that this is a Kant vibration, and then if ever so the point here. So what I did write with a star, that is delta 0, in fact. And so now if you take two points of your favorite Kant complex and you pull back, now you can define it here by pulling back. And now you have a Kant complex of equalities. Yeah? And now this is the Kant complex of passes with starting point x and end point y. Yeah? And that's what equality means. And that means now that if you have two Kant complexes, this now is the Kant complex of homotopy equivalences. Between x and y, except that maybe I won't, I will say it orally. So to have it well behaved, you have to take the appropriate definition of isomorphism. And the appropriate definition, despite what we are used to, is not that you have a map the other way so that all composites are identities. You have two maps, the other ways, and one is a right inverse and the other one is a left inverse. And you don't claim that they agree. You let the theory do it for you, but you don't force it. Yeah? And actually, this is the equation you must write down. And so if you do ordinary mathematics, there is no difference up to isomorphism, and then who cares? But if you do homotopy theory, that is, you have a non-trivial way to identify things, this matters, and this is how you should define this guy. But apart from these little details, so it's still something a nice, well-defined object. But now you see, it's not about isomorphisms anymore. It's about homotopy equivalences. And now we could still try to prove univalence. And the way I stated it, I think it's not a theorem of Voevodsky actually, because it was very. So if you prove it, if you say it in the absolute context and so forth, I think it's Bausfield who did that actually in some email correspondence with Voevodsky. But then Voevodsky, because one of the problems was not only to formulate univalence, because univalence, the way I did formulate it, if you remember, is it still there or no? I did. It was something like this. You had the actual equality, and then this, and you had the map. And the problem is to define this, and here it doesn't. In this formulation, whatever I mean by these symbols. X and Y are just types, arbitrary types, and I don't need to know that there is a type of types. I don't need to know that there is a set of sets or a Kant complex of Kant complexes and so forth. So if you formulate it this way, without mentioning a universe of everything, it is a theorem of Bausfield, but the theorem of Voevodsky was to actually produce a Kant complex of Kant complexes. global thing. And then to prove that from this global thing, you could prove this statement in any context in the setting of classical homotopy theory, and therefore that really validates homotopy type theory in classical mathematics. Yeah? In a way where now there is no difference between having an homotopy and an actual equality. And that simplifies a lot, because you see, what it means is that you have a bunch of formulas and statements, when equality, it is a Leibniz principle, which says that if you have A equal to B, in any formula when A occurs, you can replace A by B, and we will never change the truth value. That's what equality is supposed to mean. And of course, if this equality, and so claiming that homotopy equivalence satisfies this principle of Leibniz is a very strong statement and very convenient, because now you can work up to homotopy in a very systematic and mechanical way. Yeah? And this is what Voevodsky proves. And so this is what univalence is about, is to provide universes where you work up to homotopy, because you cannot do anything more strict if you want univalence. But now there is still another problem, is that, so as I said, we don't know how to do category theory from there, from the axioms only. Yeah, of course, if you do ordinary mathematics, you can, but that's cheating. You see, you are using external language. So if you want a pure way to have access to category theory, we don't know how to do it. And then, again, if you do homotopy type theory with univalence, so for each Kant complex, this will be a semantic interpretation. So that is very convenient for what reason I said. They can really play with terms in a very free way. But that prevents you to be a semantic interpretation of category theory, because you have too much adjoints that exist. Like pullbacks have right adjoints and stuff like that. So you have to, the idea now will be to do something in between when you work with univalent kind of things, but you put some restriction on the kind of gamma for which we have pullbacks, for which pullbacks can have. Actually, it's not on gamma, but the morphism between types. You want a restriction on the morphisms, so that only for those morphisms, pullbacks will have right adjoints. Will be Condorcet if you want. Okay, so otherwise I will start from another hour. So I thank you very much for your attention.